All right, welcome to the final podcast for thermodynamics section unit. Hopefully, it's getting close to spring break, or if you're moving very quickly, you're done with it now. So, learning targets for today are going to be in a calorimetry experiment. Use the heat equation to find the heat absorbed by water, then find the heat of the combustion per gram of fuel. Also, given the name of a formula of a hydrocarbon, write a balanced equation for its combustion, including the heat term. Which again, these are just all previous stuff that we've done before. Here's a little bit newer one that we're going to do dealing more with the enthalpy of everything. I'm going to use unit conversions to calculate how much heat will be produced by burning a given amount of fuel. That'll actually be the last question we do today for this podcast. So very simple and easy things right here. Enthalpy, not very hard, is just the change of heat. This is the delta symbol. That's all it is, right? Right here, delta. So enthalpy is just the change of heat, either exothermic or endothermic, all right, which will come into play here in a sec. Endothermic obviously will be a positive change in heat. Exothermic will be a negative change in heat. Here's our example problem. Bill Nye decided to take 1.36 grams of hexane and combust it in a calorimeter holding 63 milliliters of water. The initial temperature of the water is 22.6 degrees Celsius, and the final temperature of the water is 44.3 degrees Celsius. All right, so a couple questions here. This should be reviewed if you guys done everything else before. First and foremost, we want to figure out how much energy in kilojoules did the combustion of hexane release. This is pretty simple. We just use our normal equation here with Q. First, you figure out the change in temperature. So the original temperature was 44.3. I'm sorry, it was 22.6. Then rose to 44.3. So subtract the two to get a temperature change of about 21.7 degrees Celsius. When we plug everything in our equation, this is 63 grams, which remember is based upon the milliliters of water, which we can change to grams based on the density, times the specific heat of water, times the change in temperature. Remember, again, we've done this before. These are the units that'll cancel here. So then you're left with just joules. You should have got 5,714.478 joules. Using significant figures, 63 has only two significant figures here. There's only two, just the 6 and the 3. So I needed to change this number. Look at this. 1 obviously is less than 5, so 5,700 is our answer. We do need to convert into kilojoules. Kilojoules, pretty simple equation here. 5,700 joules. You have 1,000 joules in 1 kilojoule. So you're just dividing that. You should get 5.7 kilojoules, which is, again, this is review from before. Pretty simple stuff. All right. Second part of this, they want to know what the heat of combustion is for the kilojoules per gram for hexane. Again, review from before. You take your kilojoules that we figured out from the last problem, divide it by 1.36 grams of C6H14, which is hexane. We got this number, again, if you look back from in the problem right here, 1.36 grams, so it's just a given. All right. When you divide the two numbers, you get 4.191, a couple other numbers after that. Because this has two sig figs of 5.7, which is smaller than the 1.36, we round this number to 4.2 kilojoules per gram, and that is going to be the heat of combustion for hexane. Third step to this problem is what is the molar heat of combustion, the kilojoules per mole, which is a little bit different than what you've done before. All you really need to do for this is take your answer to the previous problem, which is 4.2 kilojoules per gram. All right. This right here is the molar mass of C6H14. All right. This is the molar mass, which I easily just took 6 times 12 and then added that to 14. Obviously with a little bit of change, it was 12.01. Units here will cancel here and here. When you multiply these two numbers together, you get 361.914. Again, because this has two sig figs, you have to convert your answer here to two sig figs. So if I look at this, 1 obviously is less than 5 again, so this is just 360 kilojoules per mole. Fourth step we have in this problem, write a balanced equation including the amount of energy for the combustion of hexane. Again, same stuff you did before when you did combustion stuff. Notice something I did here, just for people that are having trouble with this. The red is originally what you would have done if you would have balanced this to begin with. You would have had 6 carbons. You would have had 7 hydrogens. The problem with this is you would have ended up having 19 oxygens, which would have been impossible with the 2 there. So what you do is you can put a 19 here, double everything. So this originally was a 1, so I doubled it, made it a 2. This originally was 6, I doubled it, made it a 12. This originally was a 7, I doubled it and made it a 14. So now this is the balanced equation. To figure out the amount of energy, the delta H in this, the enthalpy, you took your 360 kilojoules per 1 mole of this, times it by 2, because in our equation here, if you notice, there's 2 moles. So you have to multiply, that's why you balance the equation, you have to multiply whatever your kilojoules per 1 mole is based upon your equation here. And I got 720 kilojoules. Now if you notice, this is the biggest change. If you need to really pay attention to this, this is a negative right here. This negative means that energy is being released. Alright, so this is an exothermic reaction. Alright, this is exothermic. The reason this is important is because if it was endothermic, you would not see the delta H in the products, you see it in the reactants. But because this is endothermic or exothermic, the delta H needs to be negative. That's what makes it. If you remember from our potential energy graphs, the delta H was always negative. All right, and finally, this is the big change to everything we're doing. This is actually dealing with enthalpy now. If 4 moles of hexane burns, before we just had 2 moles, how much thermal energy is released? All you need to do with this is just take your moles that you have here, times it by the 1 mole calculation that you figured out from before. And if you notice, these would cancel. All right, you're going to be left with kilojoules. It was around 1,440, which I then converted to 1,400 kilojoules again because you have 2 significant figures and 360. All right, this 0 doesn't count. It's a trailing 0. So again, I look here. This is where I'm going to look around. 4 is less than 5, so it's 1,400. Again, this right here, it has to be negative because it's energy being released. All right, so congratulations. Now this has been the final podcast of this unit. Enthalpy is done. You can now go on to the practice of page 27 and work on that. And then after that, actually do the review for the thermodynamics test. What do you think, Bill?